let's try to solve this question over here. The common isotope of uranium, which is uranium-238, has a half-life of 4.47 times 10 to the power of 9 years, and decaying to thorium-234 by alpha emission. Okay, so uranium-238 is a very famous radioactive nuclei, usually involved in usually used in our nuclear reactor, okay, to produce energy. So uranium-238 has a half-life of this much, and it decays to 234 thorium. Okay, so the half-life is somewhere over here in our mind map. Not my map, just this equation map. So what is the decay constant? Decay constant is lambda, so you can see that it's directly related to this equation over here. So that allows us to solve the first question, A. Okay, so A, you can find the half-life. You are given the half-life, then you're asked to find the decay constant. Again, be very careful, be very mindful of the time unit that you use. In this case, if you substitute in your time unit to be 4.47 times 10 to the power of 9, you have to remember that it's in the unit of years. So later on, when you calculate your lambda should be in the unit of per year. Okay, why? Because ln 2 over here is dimensionless, whereas the half-life here is in the unit of year. So if you do your unit conversion, if you observe the unit carefully, you see that lambda is equals to per year in this case. Okay, so if I calculate it, I should be able to get 1.55 times 10 to the power of per negative 10 per year. Okay, but usually this value here is seldom very useful. I'll usually convert it to be in per second instead. Okay, so I'll do a unit conversion here. Per year will be put at the denominator, that's 1 year. Okay, so I'm going to eliminate the year. I'm going to change it to a second. So 1 year, there's 365.25 days. Each day you have 24 hours in it. Each hour you have 60 minutes in it. Each minute you have 60 seconds in it. So if you do your conversion, you should be able to get lambda to be 4.91 times 10 to the power of negative 18 per second. Okay, we don't write lambda as back-row usually, you just write it per second. Activity you can write in Curie, you can write in back-row, but lambda usually is per second or per year or per minute per hour, whichever that is suitable. Okay, next, what mass of uranium is required for an activity of 1 Curie? So you are given your activity to be in 1 Curie, and they are interested in the mass. Mass is in this equation over here. So therefore, you know that to relate between activity and mass, you involve one equation and two equations over here. So since we are given with the activity, maybe we should start off with this equation. Because we have activity, we have lambda from the previous question, you can calculate n. Then from n over here, you can use it to determine our mass of radioactive material. Okay, so that's the approach that we are taking. So for question B, you have A is equal to lambda n. Again, when you use this equation, be very mindful of the kind of unit that you're putting in. You're putting in your activity in Curie, but you know that Curie, you have to change it to be in per second. You change it to be in per second, only you can match it with the lambda decay constant that is in the unit of per second. Your A and your lambda need to be in the same unit because n over here has no unit. So A and lambda same unit, we change it to per second, per second. So 1 Curie over here is 1 Ci, but we convert it by eliminating Ci, introducing becquerel. So 1 Curie is 37 billion becquerel, and that allows us to switch it to per second for activity. So we have settled the conversion of activity to be in the unit of per second. We have to make sure the lambda, we keep the time unit consistent by using per second for lambda. Okay, if you put in per year, that is where your time unit starts to be inconsistent and you get a wrong answer. Okay, so this is lambda. You can calculate n from here. So you can get the number of radioactive nuclei to be 7.53 times 10 to the power of 27 nuclei. Okay, so this means by you need this many nuclei in order to have an activity of 1 Curie. So that means by if you have this many nuclei, this many uranium-238 nuclei, then only you'll be observing 37 billion decays happening per second. Okay, so the more number of radioactive nuclei you have, the greater the intensity of the decay happening per unit time. Okay, that's the relationship for this equation here. Okay, so once you have the number of radioactive nuclei, you can proceed to determine the mass of the radioactive material. The mass of the radioactive material can be determined quite easily using this equation. Okay, you have 7.53 times 10 to the power negative 8 times 10 to the power 27 nuclei. That's your N. Your mass of material is what you want to determine. But you need to have your molar mass and your Avogadro number. You are not given the molar mass explicitly, but as I mentioned, the molar mass can be obtained from the number of nucleon or the mass number. Since the mass number of the radioactive nuclei is 238, so it's not 234 thorium because 234 thorium is the daughter nuclei. 238 uranium is the parent nuclei. So which one is the unstable nuclei? Which one is the radioactive nuclei? It is the parent nuclei that is the unstable radioactive nuclei. So our radioactive nuclei is 238 uranium, not 234 thorium. Of course, 234 thorium will be a parent nuclei for further decay to other stuff. But for this particular reaction that we are studying here, the parent is 238 uranium, the daughter is 234 thorium. So we are interested with the radioactive nuclei, which is the one that is decaying, so that's 238 uranium. So 238 over here is the mass number, it is the number of nucleon. So if we attach a unit of gram, then that will allow us to determine the molar mass for 238 uranium. Just attach a gram, then 238 gram over here will be the molar mass of uranium. So 238 gram, be very mindful of it. If you want to avoid mistake right now, you can convert it immediately to kilogram. That's fine as well. So you can put times 10 to the power negative 3. So you are able to get your mass in kg. Because 238 here is in gram. If you times 10 to the power negative 3, you change it to kg. Okay. So you have 6.02 times 10 to the power of 23 over here. So if you calculate your mass, you'll be able to get the answer of 2.977 times 10 to the power of 3 kg. Okay, so that is the mass required, the mass of uranium required in order to have this many nuclei in it. So if you have 2.977 times 10 to the power of 3 kg of uranium, then you have this much of nuclei in the uranium material. And if you have this much nuclei, this many nuclei in your radioactive material, then you observe 37 billion decays happening per second. Okay, so that's the idea that relates between these two equations over here. Okay, question C, how many alpha particles are emitted per second by 10 gram of uranium? So now they're giving you the mass of uranium and they're asking for how many alpha particles are emitted per second. So how many alpha particles are emitted means by there's how many decays that are happening per second. Because every one single decay that happens causes one alpha particle to be emitted. So one decay is equals to one alpha particle emitted. So when they are asking how many alpha particles emitted per second, that is equivalent to asking how many decays happening per second. So decays happening per second is equivalent to activity or decay rate. So they are asking for A actually. They are asking for A, but you have to relate it from the mass of uranium. So just now we are going from this equation to this equation. Now we are going in reverse. We start with the mass equation, get our number of radioactive nuclei first, and from there we get our activity. Okay, so we are going in the reverse order comparing to question B. Okay, so question C, I don't think I have a lot of space. I'll start with the equation to determine the number of radioactive nuclei. So mass divided by molar mass multiplied by the Avogadro number. I'm given 10 gram, I will convert it to kg, so 10 times 10 to the power negative 3, this is in kg. And my molar mass is 238 gram, but I convert it to kg as well, times 10 to the power negative 3. I just prefer to change things to be in SI unit, even though I don't think it's necessary in this case because 10 is in gram, molar mass is in gram, so gram will cancel each other out as well. But it's just a habit for me to convert in SI unit. Okay, so multiply by the Avogadro number, so that is 6.02 times 10 to the power of 23. Okay, so from here I can determine the number of radioactive nuclei to be 2.529 times 10 to the power of the 22 nuclei. So this is how many uranium-238 nuclei that I have if I have 10 grams of uranium. It's quite a lot of nuclei actually, but that is not where we should stop. We are asking for the how many alpha particles are emitted, or we are looking for activity. So we have to proceed to use this equation to determine activity. So lambda, we'll use the one in per second, so that our activity will be in per second as well. So in per second, it will be 4.91 times 10 to the power negative 18, multiplied by the number of radioactive nuclei fresh from oven, 2.529 times 10 to the power 22. So here, because the unit of lambda is in per second, later we multiply it with n, which has no unit, our activity should be in per second as well. So per second, the answer for per second activity is equivalent to becquerel, right? So you can write our answer in the unit of becquerel. And of course, if you choose to, you can convert it to in curie as well, but I don't think it's necessary because they're asking for per second, right? How many alpha particles are emitted per second? So per second is equivalent to becquerel. So this is how many alpha particles emitted per second. But if you feel like you are not answering the question directly, you can write a statement somewhere here. Okay, so you can say 1.24 times 10 to the power of 5 alpha particles emitted per second. Okay, just to make things clear, because decay rate, people might not see it to be directly related to how many particles, how many alpha particles emitted per second. So because you know that one decay is equivalent to one alpha particles emitted, so you can say that the same amount of value of alpha particles are emitted per second. Okay, so I think this is also a very interesting question because it relates between many different quantities that involve half-life, decay constant, activity, and mass, all in the single question. So I think it's a good practice to use this question to understand how all of the equations are used to relate between the different quantities. So that's it for this question. Thank you very much.